first two, but some of that depends on questions and everything else. So this is a very different way for understanding matrix Rademacher series that was developed in a paper called Matrix Concentration Inequalities. Via the method of exchangeable pairs. Which was written with Lester Mackey, Mike Jordan, two of my group, Richard Chen, Brendan Farrell, and me. Okay, so the principle that I trace back to the work of Alsved and Winter is their idea that you can take methods for proving scalar concentration inequalities and lift those arguments to the matrix setting. Scalar argument, capitalize things, and with some amount of effort, you can repeat the argument for matrices and get a matrix equivalent. Okay. Now, there's a beautiful approach to scalar concentration due to Sourav Chatterjee. It's in his thesis, and there's a paper from 2008 where he uses the method of exchangeable pairs due to Charles Stein from 1972 to establish some concentration inequalities for scalar random variables. So this is maybe not so familiar, so I'm not going to go through the scalar version of the argument, but I'll spend a bit of time on the details so you can see how this works. Because it turns out that this argument lifts to matrices without any fancy equipment like Lieb's theorem and leads to some extraordinarily simple proofs of some very deep results. So we're going to use a matrix version of this idea to prove something called the matrix Khintchine inequality. I'll tell you what that is in just a minute, but it's a moment inequality for Rademacher theory, Rademacher series. Okay, so here's the result. So there are a lot of names attached to this. OC. This is due to Françoise Luce-Picard from 1986. There was further work with Gilles Pizier in 1991. There's a paper by Arthur Buchholz in 2002. And so these are all different versions of this. All right, so what's the setting? We've got some fixed Hermitian matrices. And we've got some Rademacher random variables, epsilon 1 up to epsilon n. These are IID. And we're interested, once again, in the matrix series obtained by modulating these matrices AK by Rademachers and adding them up. Okay, so the result is that if you're interested in computing trace moments of this random matrix, there's a bound. So the 2pth trace moment is bounded by root 2p minus 1 times the expectation of the trace of x. Sorry, it's in the wrong place. This is the trace of the expectation of x squared to the p power to the 1 over 2p for p equals 1, 2, 3, and so forth. So the bound I'm going to prove is just for integers. This leading constant here is within a factor of root e of sharp. So this is about as good as this kind of result gets. And remember, this guy here is the sum of the AK squared, just like in the last lecture. All right, so what does this result tell us? It says that the trace moments of this Rademacher series grow like the moments of a standard normal variable. Okay. So remember, these are roughly 2p to the p. Same here.
So this is known not to be true for all p larger than or equal to 1?
It's true for the constant changes a little bit, maybe, but this is known to be true for all p greater than or equal to 1. I'm just proving it for the integers because it's a little easier. Okay. So for those in the real analysis program, this is what you might call a hypercontractive inequality for matrices. Okay, so it just says that the moments decay really the moments don't grow too fast. And if you're interested in controlling the spectral norm, you can use the fact that trace a to the p to the 1 over p is roughly equal to the spectral norm of a if p is equal to roughly equal to the log of the dimension of the matrix A. So these powers, trace powers, are not so different from the spectral norm for large enough powers. Okay, so this allows you to get bounds on spectral norms as well. Do lots of other stuff. So the reason this result is powerful is because you can combine it with symmetrization arguments. So we're not going to get into this, but you can replace zero mean random variables, in some case by the same variable multiplied by a Rademacher variable, and then compute conditional bounds by averaging over the Rademachers. So you can do lots and lots of stuff using this kind of technique. All right. Any questions on the statement of this result?
So you're going to prove it, right?
We were going to prove it. All of us together. Anything else? Okay. By the way, you can extend this to rectangular matrices, just like we did in the last hour. So this is actually even more general. Okay. So the method of proving this result.
And in the
Sir?
scalar case, this reduces to the Khintchine?
Yeah. The constant's not quite sharp, but so in the scalar case, this is just the Khintchine inequality. Of course, the Khintchine inequality is elementary. This proof is elementary, actually, more or less, but it's only because of some very clever ideas due to Chatterjee.
So,
Yes.
So just can you remind me why we want to study this theorem?
No. No, actually, I would rather not get into that because it's already late in the afternoon. I've been talking for a long time, and doing another example would take another 15 minutes. So the same applications that the last result on tail bounds for the Rademacher series, this is an even sharper version of that result. So that's one way to think about it. You can prove those same tail bounds using this type of... I don't mean to be dismissive. I'm happy to talk with you more tomorrow, maybe. Anything else?
The motivation's the same. It's just a different method to prove something sharp.
Motivation's the same.
Basically.
Yep. Exactly. But I mean, I didn't really motivate why you would care about a Rademacher series to begin with. But what can you do? All right. So let's get started on this proof. So the first definition is one that's familiar to probabilists, and that is an exchangeable pair. So I'm going to be a little bit sloppy about all of this stuff because I don't really feel like the rigor adds all that much. So a pair ZZ prime of random variables is exchangeable if the distribution of ZZ prime is indistinguishable from the distribution of Z prime Z. So, all right, these two random variables cannot be distinguished from each other in some sense. All right? This is not to say that these variables are independent. The marginal distribution of Z and the marginal distribution of Z prime must be the same in particular, otherwise you'd be able to tell them apart, right? But Z and Z prime can be very closely connected. Okay? It's just that averages and other functions, depending on these variables, don't change when you swap the variables. Okay?
It's conditioned on any other variables.
That's right. Yeah. So, basic definition, and now we have another definition which is rather less familiar. It's called a matrix Stein pair. So a matrix Stein pair is a special kind of exchangeable pair consisting of matrices. So we're going to let X and X prime be an exchangeable pair of Hermitian random matrices. Okay, so each of these two members here is a random matrix. Each one is Hermitian, and they have the same distribution. All right. Then we say that XX prime is a matrix Stein pair if we have the following reproducing property. The expectation of X minus X prime, conditional on the sigma algebra generated by X, is equal to alpha X for some alpha between 0 and 1. Okay. Yikes. So what does this mean? In some sense, it tells us that the differences between X and X prime reproduce X. I'll do an example in a minute that might make this a little bit clearer, but frankly, this definition has some amount of magic in it, and it's that magic that makes everything work. Okay. The key point, though, is that if we fix X and then average out over whatever randomness is left in X prime, we spit out a scaled copy of X. Why would you believe that such a thing is interesting or that it even exists? Well, because there's an example. So the example that we're going to use is a Rademacher series. So
if they're independent, alpha is 0.
yep.
It's beginning to
No, alpha is 1. If they're independent, alpha is if they're independent, alpha is 1. Right? So
okay, yeah.
because X in particular, it turns out X prime would have to be equal to 0. The mean of X prime has to be equal to 0. But okay. So the idea behind all of this is that if we can construct good matrix Stein pairs, we can establish concentration inequalities for X. Okay, so you should think about someone handing you X, and it's your job to produce the exchangeable counterpart X prime. And good in this context means that, well, X prime had better have the same distribution as X, and X prime will also need to be close to X. So this means same distribution, this means close to. All right. So let's do an example. In some sense, this is the most important example, which is probably where all of this came from in the first place. And that is our matrix Rademacher series. So in this case, X is the sum of epsilon k times AK. And we're going to construct X prime by picking a term from X at random and getting rid of it. And then we have to put it back. But we'll replace it with a fresh copy of the randomness in the Rademacher variable. So here we've got a uniformly chosen index. So we're picking one entry from this sum to knock out. And epsilon prime is an independent copy of epsilon. So these are all fresh Rademacher variables. Okay? So we knock out the ith term from the sum, and we replace it by another copy where we put in a fresh Rademacher. Okay? So you can see that this is not so different from x because we've only changed one term. And sometimes we don't even change that. And obviously these guys have the same distribution because all we've done is swapped out the randomness in one of these epsilons for fresh randomness. Okay? So same distribution, close by. All right. So let's check this condition. Find out what the scale factor alpha is going to be for this example. Oh, you're right. So you can apparently identify the scale factor by pure thought. All right, so what happens? Well, we have epsilon I minus epsilon I prime times AI being the only term remaining after we subtract. And now let's first average over the i's because we're not allowed to average over these epsilons. So this is the expectation of the sum from I equals 1 to n of epsilon I minus epsilon I prime times AI conditioned on epsilon. Well, now this is easy. We're not allowed to average these guys out. These guys have mean 0 because they're independent from this. Well, all right. And we conclude that, in fact, this reproduces the original series. So it turns out that, is there a question? So it turns out that this is not the only example. Independent sums more generally can be subjected to the same treatment. There are other kinds of examples you can do as well, bounded difference type settings and so forth. But I want to focus on this simple example here. And you can see that the key point is that we found an exchangeable counterpart of the random matrix that's very close by just by knocking out one of the coordinates and refreshing it. All right. We'll see, I hope, why it is that this is a useful thing to do in just a moment. And so this is the value of alpha. Okay, good. So the key result is that we can use Stein pairs to compute expectations. All right. So the result is a lemma known as the method of exchangeable pairs. And the method of exchangeable pairs takes as its input a matrix Stein pair. And f, a matrix valued function. And what it tells us is that we can compute the expectation of the form x times a function of x. So this takes x and spits out a random matrix, a matrix of the same size, as 1 over 2 alpha times the expectation of x minus x prime times f of x minus f of x prime. All right, so if we have an expectation of this form, it can be rewritten like this. Now, let's stare at this for a moment and try and understand why it is that that could be a useful thing to do.
X prime, the matrix Stein pair f of x at x prime also, or for some f?
Excuse me?
Can we say anything about f of x prime?
Um,
Whether they are matrix Stein pair or not?
Not with this method. Why don't I do the proof first, and then we'll talk about why this is an interesting argument. All right, so here's the proof. Alpha times the expectation of x fx can be rewritten as the expectation of the conditional expectation of x minus x prime conditional on x times f of x by drawing the alpha in here and then using the definition of a matrix Stein pair. All right. Now, this is constant once we know this sigma field, so we can draw this inside the conditional expectation and then combine the conditional expectations. So we'll obtain the expectation of x minus x prime times f of x. So this is just usual manipulations with conditional expectations. This is constant as a function of x. And then once this is inside, we use the tower property to get rid of the conditioning. Okay. All right. Now we can do the same thing again. But now we're going to use exchangeability to switch x and x prime here. So this expectation does not change if we swap the identities of these two variables. So this is exchangeability. All right. Now we're going to...
Let's say if you add them and you get this.
Hmm?
Let's say if you add them and you get this.
We're done. All right, average these two things and we're finished. Okay, good. So here are two examples. So first of all, what if f of x spits out the identity matrix? Well, that tells us that this term is 0. And so we see that the expectation of x is equal to 0. So in other words, a matrix Stein pair always consists of 0 mean random matrices. All right, so you can't construct one of these otherwise. The other interesting example, which is really where this comes from in the first place, of f of x is the identity map that just spits out the matrix x, in which case this result tells us the expectation of x squared is equal to the expectation of x minus x prime squared. So times 1/2 to alpha. Thank you. So in other words, this gives us an alternative way to compute variances. All right? And this is really where these ideas come from. So this is a version of the Stein inequality. If you're familiar with that result, or the Stein identity. Okay, good. Now, why would this sort of thing be useful more generally? The answer is in the structure of this expression and what we mean by a good matrix Stein pair. So, what property does a good matrix Stein pair have? Well, we've assumed that x and x prime are close to each other, right? That's what we hope to achieve. So if x and x prime are close, this term is small. And if x and x prime are close and f is kind of Lipschitz, this guy is also small. So we can exploit the fact that the hope, at least, that x and x prime are similar plus the Lipschitz properties of the map F. And we want to use those to bound expectations or rewrite expectations of this type. And that's really why this is productive. All right. So next, we've got one more lemma that shows how this plays out for these Rademacher series. This is what we'll call the mean value trace inequality. So this says that if A and B are Hermitian matrices, and P is a natural number, then the trace of A minus B times A to the 2P minus 1 minus B to the 2P minus 1. So this looks a lot like that. Can be bounded as 1/2 times 2P minus 1 times the trace of A minus B squared times A to the 2P minus 2 minus B to the 2P minus 2. Okay. So this is going to allow us to take an expression of this form and provide an upper bound for it in terms of a difference squared. So this will be like a variance term, and this should be a plus sign. All right. So I think in the interest of time, I'm not going to even prove the scalar version of this for you. This is based on the Hermite representation of a divided difference. And a result called the generalized Klein inequality that allows you to lift scalar inequalities to the matrix setting. This is really easy to prove. This is completely elementary, even in the matrix case. There's nothing fancier here than an eigenvalue decomposition going on in the background. So, all right. Now, yeah. I mean, you can extend this to all real numbers without too much work, but there's more notation you have to carry around. So, I mean, basically you're using the fact that those even powers are convex and on the real line. And so if you didn't have an even power, you'd need some absolute values and some signums and some other.
If there is a way to make
yes. Mm-hmm. Yeah. All right. Now, this allows us, these tools that I've described allow us to prove a result for matrix Stein pairs. It's called the matrix Burkholder Davis-Gundy inequality. And this is from the paper that we wrote. And it follows an argument that was set out by Saurav Chatterjee. So we'll let X and X prime be a matrix Stein pair. And we'll define a quantity called the conditional variance, delta X, which is 1 over 2 alpha times the conditional expectation of X minus X prime squared conditioned on X. Okay? So you should think about this like the norm of a gradient. So X minus X prime is an estimate for how rapidly the random matrix is changing near X. You're squaring it. And so this is roughly a norm of a gradient. The alpha is dividing out by the scale. So it's just a heuristic. So if you're familiar with things like log Sobolev inequalities, this is the norm of the gradient that turns up there. Okay. So the result that we have is that the expected trace of x to the 2p to the 1 over 2p power is bounded by root 2p minus 1 times the expectation of the trace of delta x to the p to the 1 over 2p power, and that this is valid for natural numbers p. Okay. So it tells us that we can compute high moments of a matrix Stein pair if we can compute slightly lower moments of this conditional variance. Okay. In the case of a Rademacher series, this is going to be real easy to compute. So we'll do that in a few minutes after we finish establishing this result. So this is really an immediate consequence of these two lemmata that we have sitting here on the board. And then to prove the matrix Khintchine inequality, we're just going to combine that with the calculation that I'm erasing at this very moment. All right. Let's go. So we're going to define the quantity of interest E, which is the expected trace of x to the 2p power. Now, we don't have anything in sight that looks like x times f of x. So we need to find such a thing. We're going to do that by peeling off a copy of x from this power. All right? Oh, look. We've got x times a function of the random matrix. And this is exactly the form that we require to apply the method of exchangeable pairs. So the method of exchangeable pairs gives us 1 over 2 alpha times the expectation of the trace of x minus x prime times x to the 2p minus 1 minus x prime to the 2p minus 1. And so this is the method of exchangeable pairs lemma. Okay, now this lemma here tells us exactly how we can bound a quantity like this. This is a deterministic result. Doesn't depend on the identity of the matrices or anything like that. So we'll just apply this. And we'll obtain the expected trace of x minus x prime squared times x to the 2p minus 2 plus x prime to the 2p minus 2. And now we're going to have to put in this factor of 2p minus 1 and also this other factor of 2 that I left out from the lemma. Okay? So this is the mean value trace inequality. All right, now we just have to clean up. We're done. So the first thing we're going to do is notice that this term here, x minus x prime squared times this power, has the same distribution as x minus x prime squared times this power because of exchangeability. So each of the two terms in this sum has the same average. So we're just going to get rid of one of them and cancel the 2 here. All right? So we get 2p minus 1 over 2 alpha times the expected trace of x minus x prime squared times x to the 2p minus 2. All right. Next, we're going to go find a copy of this conditional variance in this expression. So we'll pull the 2 alpha inside here and split the expectation into the part conditional on x and the part where we average out x prime. So this will give us 2p minus 1 times the expected trace of delta x times x to the 2p minus 2. So identify delta x. All right, now we're going to apply Hölder's inequality for the trace, and then we're going to apply Hölder's inequality for the expectation. And that'll give us 2p minus 1 times the expected trace of delta x to the p to the 1 over p times the expected trace of x to the 2p to the p minus 1 over p. So this is Hölder twice. All right. What have we found here? See this guy on the board anywhere?
You cancel it.
Just up at the top. So we've got an algebraic relation for the quantity that we're interested in. So we'll divide through, we'll raise to the appropriate power, and we'll conclude that e to the So E is less than 2p minus 1 to the p times the expected trace of delta x to the p power. That's the result. Did I make a mistake?
There is an
There
alpha.
was 2 alpha in the denominator.
The 2 alpha is now sitting inside the delta x. It's part of the definition. Yeah. All right. Any questions on that calculation? Because this is really
It's an analog of symmetrization, except
Yep.
now we have an exchangeable
Yep.
pair instead of independent.
exactly. And the interesting thing is that they can actually have a lot to do with each other, and that's what makes this work. The fact that x and x prime can be very, very close. All right. Good. So we've established this result, and now we can prove the matrix Khintchine inequality. By the way, this is the most elementary proof of this result that I know. All right. So yep. X is equal to the sum of epsilon k times ak. X prime equals x minus epsilon I ai plus epsilon I prime ai. And so now we need to figure out what delta x is. So delta x is equal to 1 over 2 alpha, which is to say n over 2, times the expectation of x minus x prime squared conditioned on x. So this is just this term here. So we get n over 2 times the expectation of epsilon I minus epsilon I prime squared times ai squared, conditional on the randomness in epsilon. First we'll average over I. So sum from I equals 1 to n. Once again, I've forgotten the normalizing factor. And now all we have to do is average out over the epsilon I prime. But this can only take two values, 0 or 2 squared. Each occurs with equal probability. So we have 1/2 times 4 is 2. That cancels the 2 here. And so when we complete this average, we see that we obtain the sum from I equal 1 to n of ai squared, which is also known as the expectation of x squared. All right. So here's the calculation of the conditional variance. In this case, it's very, very easy, and it really just produces the variance of this random matrix. All right. Now all we have to do is substitute this result into the matrix BDG inequality, and we obtain the expectation of the trace of x to the 2p to the 1 over 2p is less than root 2p minus 1 times the expectation of x squared trace to the p to the 1 over 2p, which is a result that we required. So in some sense, this matrix Khintchine inequality, I realize I didn't spend a lot of time motivating this for you, somehow is more powerful than all the other results that we've talked about, and that if you don't care about the constants, you can derive almost all of them by clever applications of this, by introducing Rademacher's through a symmetrization process and then applying this inequality. So it really is very powerful. And this was something that was really appreciated by Gilles Pizier, and it found its way into the work of Rudelson in 1999, where he used this technique to study the sample covariance problem that I started out with in the first lecture. So The cool thing about the method of exchangeable pairs is that it provides a very elementary proof for this result, even in the matrix setting, and it gives you a constant that's within a factor of root e of optimal. You can't really improve this very much. The other really attractive thing about the method of exchangeable pairs, as opposed to some of the other techniques we've talked about, is that it extends from independent sums to other kinds of random matrices that are based on somewhat dependent random variables. And the reason is because we can construct these matrix Stein pairs somewhat more generally than in the case of an independent sum.
What's the martingale?
So it's not exactly the same as a martingale. It doesn't have that directional flavor that a martingale does, but you can prove bounded difference inequalities this way. And that's actually pretty straightforward. It's basically the argument that I just showed you. So I'm going to stop now, see if there are any more questions, and then I'll let y'all continue on to your happy hour.
Is there a reverse version of the inequality? In the scalar case, we have the opposite version as well, right?
Yeah, you have the lower bound without the factor of root 2p minus 1.
Yeah.
And so what that tells you is that the only loss in this inequality is that square root 2p minus 1.
So the lower bound still holds in the matrix case.
I mean, more or less. You have to do some extra work, but it certainly holds for the square.
Okay.
Actually, no, it's right this way, too. Yeah, it's just Jensen's inequality.
Okay, yeah.
Any other questions?
I just had a quick comment about, I really think this is a wonderful thing that everyone should know more about Stein. And just looping back to the early part of the day, Stein developed all these ideas to prove the James Stein, the optimality of the James Stein estimator. It was all tied up in his mind. But if you'll see in Joel's presentation, there was never a mention of independence. There was never the exponential. It's just it's an in-run around the kind of usual Fourier method you use to prove central limit theorems and large deviations you saw, just completed for technology. And so independence is not needed. You can get by with some dependence. And the other point is that Joel's example, I mean, use Rademacher very effectively here because you can do all the calculations in 30 minutes. But Rademacher is just simple sum where you take out one and you take out one part of the sum, one sum and you put in a new one. But think more generally, you have some combinatorial structure, a graph, say, or some other combinatorial structure, or some algebraic structure, where it's natural to take out something and put in something else in a random place. And so I think you can well imagine, and in fact, these ideas will apply to all kinds of other objects that combinatorial people and algebraic people might be interested in getting the concentrations out of Stein for the same kind of reasons with the same kind of elementary ideas. So I highly encourage you, if you haven't learned about this stuff before, to spend some time with it. It's going to be a technology I think you'll see a lot of in the next 20 years.
And it should also be said that Chatterjee's paper really is kind of miraculous. He managed the it took us 45 pages to do this in the matrix setting, and it's not because our argument's any harder, it's just that he was so much more economical in his presentation. In 15 pages, he's developed, all of these results in the scalar setting, exponential concentration, polynomial moment bounds, and applied them to 4 different examples involving spin glasses and other problems in graph theory. It's really a tour de force. And
so that paper is in probability theory and related fields, I think?
Yeah, I think that's right.
Pages and
yeah.
So actually there are books on Stein's method. If you'll pick one up, it's kind of like the random. It looks complicated. That stuff is all for distributional results, not for concentrations. So trying to get the whole distribution, not just trying to get tables. Chatterjee, I think, was the first person with the insight to that same way of thinking, stripped down to bare essentials, basically coupling ideas and exchangeability is enough to get the concentrations without trying to aim the whole distribution much more.
And what I'd like to emphasize is that this presentation here, this entire argument, was envisioned by Mike's student, Lester Mackey, and he developed the entire version of this argument, applied it to matrices, and developed this wonderful proof of the non-commutative Khintchine inequality all by himself. He's in the statistics faculty at Stanford now, so his reputation preceded him, and I think that he's also someone that is worth paying attention to. He's done great work on this problem.
Okay, that was a lot in one day. Let's thank Joel again for See you tomorrow morning.